So at this point, we've exhausted all of the analytical methods that we have for solving first-order differential equations. So what do we do now? Well, we're going to look at something called a numerical method for solving a differential equation. And when I say solving it, what I really mean is that we are going to approximate the solution to it. So it's not going to be exact like we get with pen and paper solutions, but it will give us a good idea of what the behavior of a differential equation is going to look like. And it really boils down in a lot of ways to some of the same ideas that we saw when we did direction fields. So it's very, very similar. So numerical methods will allow us to approximate, I really can't write today, allow us to approximate the solutions of ODEs. And in fact, there are methods for solving or approximating the solutions of PDEs as well, and they're based on the same methods that we're going to learn here. So how do we get started with this? I want to start with an example, and then I want to think all the way back to Calculus 1, where we basically defined a derivative because our differential equation is going to involve a derivative. So let's start by considering a generic example here. So consider the first order ODE given totally generically by, let's say that it's y prime equals some function of x and y. And we don't know whether this winds up being linear in y or if it's nonlinear. All we know is that it's a first order differential equation. And let's give ourselves an initial condition. Let's say that y at some value x0 spits out a value of y0. So there's our initial condition. So what I want to do is go back and inspect this part of our equation, the derivative right here, in a very similar way that we first defined the idea of a derivative back in Calculus 1. So recall our definition of a derivative, the limit definition from way back in Calc 1. It's probably been a while. The derivative, so if I want to call it y prime in this case, that's fine, is equal to the limit as some parameter. Sometimes we used h, maybe we use delta x. It doesn't really matter. I'm not sure what our book uses. If they use, I'll call it delta x. So the limit as delta x goes to 0 of the following. We'll take y and evaluate it at basically some point x plus delta x. And then we'll subtract off y at x, and we'll divide the whole thing by delta x, and again take the limit of that. So basically, the idea is, and we'll draw a picture of this in a minute, this is a slope. It's a small amount of rise, a difference between the y value at two different x coordinates, so at x and then a little bit past x, so delta x past x. So the top is basically a rise, a difference in two heights, and on the bottom we have a run, a difference between the two x positions. One we looked at position x, the other one was x plus a distance delta x. So delta x is how far is between these two x coordinates. So this is an exact representation of what y prime is at a given x value. But that means that if we take away the limit, this is no longer exact, but it is a good approximation. So removing the limit makes this an approximation. So basically what I'm suggesting is that y prime is approximately equal to y at x plus delta x minus y at x divided by delta x. And for small values of delta x, when delta x is small, i.e. up here when it's close to 0, this approximation is going to be pretty decent. And the smaller we make delta x, in fact, the better the approximation is going to be. So this is a good approximation, or a decent approximation, when delta x is small. How small? Well, that kind of depends on how steep the curve is, all these various things. So we'll just say generically, it's going to be good when delta x is small. We're going to use this approximation. So what I'm going to say is, instead of solving the differential equation the way that we have it set up here, I'm going to solve this differential equation, or approximate the solution to this differential equation, by replacing the y prime term with this approximation. So if we plug this into the ODE, or substitute it in, I should say, to be slightly more formal, if we sub this into the ODE, we get something that looks like this. So I'm going to get y at x plus delta x minus y at x over delta x, there's my left-hand side, the y prime term, is equal to some function of x and y, which was our original right-hand side, if I can scroll up and remind you here. So this is basically what we're looking at. I can just algebraically rearrange this in a way that's going to be convenient. So I'm going to multiply both sides by delta x to get rid of the fraction. If I multiply both sides by delta x, I will wind up with y at x plus delta x minus y at x is equal to f of x comma y times delta x. And if I move this term over to the other side, I wind up with the following. So I just get that by adding y of x to both sides. And this is actually the stage that I want to stop and look at. Why did we algebraically rearrange things here? Well, if I look at basically what we've set up here, what I can do is plug in a known value of y at position x. Oops, and I need to erase this. I wrote the wrong term there. That's not delta y, that's delta x. Sorry for any confusion there. But basically, this is prescribed in the original ODE. Delta x is some small parameter that we get to pick, and y of x is something that we also potentially know. For example, we have an initial condition, so I know that at this particular value of x, I know what the corresponding y value is. So I have at least one y of x that I know. I can use these, so basically I know this, and we get to pick this. And I can use all of those to then get a guess at what the next value of y is going to be at the position, not x anymore, but a little bit past x, delta x past x. And it'll give me an approximation for the next value of y. So if I start with the initial condition and plug that in here with the known given value of x and y at that initial condition, and I plug into this formula, it'll spit out a guess for the next value of y that's going to be relevant at this corresponding x value. I can then recycle those terms back into the formula, and so I'll know a next x term, plug in those next x and y values, and run through the machinery to spit out yet another guess for the next value after that. And we can repeat this process over and over to get a successive number of guesses of all the different y values at all of these different x values. So we'll see that in just a minute. But let's look at it for just this one step, and let's look at it geometrically. This will probably give us a little more insight. So let's say we have a graph. Here's my x-coordinate and my y-coordinate axis. And let's say that we have some real solution. This is the thing that we don't actually know, but that we're trying to guess. So this is the real solution curve. And let's say we know some point right here. Maybe this is the point right here that we know. This is our x naught comma y naught point that we know is on the real solution. So this is basically our initial condition right here. What I want to do is basically try to get a guess for the next value. If I look at this equation up here, what I would do is basically plug in the x naught and y naught values into this equation. It will give me the slope at this point. So really coming back up to the original equation, if I know a given x and y value, and I know that y prime is equal to f evaluated at that given x and y value, then what it's essentially saying is I know the slope at that exact point. This was the idea behind direction fields. We know the slope. Pick an x and y coordinate, plug it in, and we know the slope there. So this is going to be the point that I pick. And I can figure out the slope there by just plugging into our function f, and it'll give me the slope. So let's say it gives me a slope that points in that direction. So we have some slope is simply going to be equal to f evaluated at x naught comma y naught. It's going to give me the slope. F represents the slope, and we're just looking at this particular point. And what I'm going to do is I'm going to follow that slope a little distance in the x direction. So I'm going to go a distance delta x in the x direction and figure out what the corresponding y value is. So this distance here, this distance here. The horizontal distance was delta x. That's how far we went in the x direction. And then it'll give me a guess for the next y value. So I take a couple of different points. Let's put them all together. So this point right here, what is the original y value at this point? We just said it's y naught. You could think of it as basically being this point, y evaluated at x sub 0. So this height right here is y evaluated at x sub 0. It happens to be y naught. So that is this height right here. We're going to plug that in, find the appropriate slope at that point, go a distance delta x, and figure out what is the corresponding rise if I were to just follow in a straight line. So basically what we're doing is a linear approximation. That's really the easiest way to think about this. This that we have right here is essentially basically our y equals mx plus b. It's the equation of a line here. And it's going to give us the next y value given a current y value. So we'll take a look at that in, again, just a minute. So this point that it's going to spit out is going to be our guess. It's going to be the new value. I guess I should not. Let's do it this way. What I really want is, come on, eraser. This y value. The y value right here is the y at basically x naught plus delta x. It's our approximate solution. This is our approximate guess. And you can see it's not exact because the real value is actually up here because we didn't take into account the curvature and the concavity of the curve. We just approximated it with a linear approximation. So this y value is the actual y value, the actual solution that we wanted. So here's a picture of what's going on. Let me convince you that this value right here, this y value, is exactly what this formula is going to spit out. So let's take a look and just think about how this works with this picture in mind. If I want to figure out the y value right here, all I need to do is basically follow we need the equation of the line. So what is the equation of the line? We're going to use point slope form. So what is the equation of the linear approximation that we've come up with? So basically what we're going to do is I'm going to use point slope form. So let me just remind you what point slope form says. It basically says that if you take y minus some known y value, this is going to be confusing. Maybe I should, am I going to get away with this? Maybe this will work. Y minus y naught equals m times x minus x naught. Maybe we get lucky here and this isn't going to be confusing after all. Okay, so this is a normal point slope. If we know a point x naught, y naught that's on the line, this is the equation of the line. And you can figure out the y value at any given x value of your choosing. So let's think about this. What is the slope? The slope is our f, and it's going to be the f at the point x naught comma y naught. So the slope, coming back up to the original differential equation, the slope, y prime, is just f evaluated at a given point. The point we're interested in is the point x naught, y naught. So it works out cleanly here. This m is just f of x minus x naught. Or sorry, f of x naught comma y naught. What about these other pieces? So let's say I want to know what is the value of y. So use this to find the value of y at the position x naught plus delta x, because that is this x coordinate right here. So let me do this. Let me do little dotted lines down. Here's the original point x naught, and here's the x coordinate of the next point that we care about. It's x naught plus delta x. How do I know it's x naught plus delta x? Because the original point was x naught, and this distance right here is delta x. So what is this point? It's the x naught plus that delta x. And it is the point that we're interested in finding the new y value at. So that is our goal. What is the y value at this new x value? So all I need to do is plug this in place of x over here. So plug in for x. And so we will get y minus y naught is equal to f of x naught comma y naught times x minus x naught. But what are we plugging in for x? We're plugging this in. So it's going to be x naught plus delta x, right? That's our value that we're plugging in right here. And then we need to subtract off x naught. And what do I get when I do the subtraction? Well, I have a positive version of x naught here. I have a negative version of x naught here. These are going to cancel. And we will get y minus y naught equals f of x naught, y naught times delta x. And rearranging it one more time, we will get that y is equal to y naught plus f of x naught, y naught delta x. So there is the equation, totally rearranged and solved for the new value of y. How does that compare to what we had right up here? It's exactly the same if I were to plug in x naught, y naught as the starting point. So this basically says if you know a given point that is on the curve, we can guess what the next point should be a distance delta x away. And here we've gone through and done that, assuming that the one point that we know is the point x naught, y naught, that we know that initial condition point. And we've plugged it in, so x naught, y naught here, delta x here. What is the initial point that we know? Our y of at the point x naught is y naught, so this is y of x naught. You could think of it like that. And what does it spit out? It spits out our next guess at the position y. So the next guess y at the position x plus delta x. So in our case, x naught plus delta x. So it's basically these are the same. With x naught, y naught plugged into the point what originally was just what we called some generic xy. So we've picked a specific point that we actually know for sure is on the curve. And so this is the idea. It's a linear approximation. This is called Euler's method. And it's basically something, if we repeat this over and over and over again, we can successively get a bunch of guesses to figure out what the solution is going to look like. So basically what we do is, again, let me just kind of give you a quick estimate. If this is the real solution on our coordinates x and y, and here's our starting point, x naught, y naught, what we're going to do is plug into this point and use a linear approximation to get a guess for the next point. And what I'm going to do there is then find a guess for what the slope should be at that point. And then I'm going to follow it a distance to the next point. Then I'm going to guess the slope there, maybe it's the same, more or less the same direction, and follow it a distance of delta x. And so basically, if you look at all of these positions, we're going to start off at the point x naught. This distance to get to the next point will be position x naught plus delta x. Then we're going to go from there to get to the next point. This will be the point x naught plus 2 delta x's, because we've now added 2 of them in. Then I'll go over and up again to get our next guess for our next y value. That point we'll guess, find the slope there, follow it a distance here, right, and so on and so forth, and just basically repeat this forever. So on and so forth, until we are sufficiently happy with our estimate. And you'll notice that this kind of line that I put together, this connect the dot line, doesn't match the real solution exactly. It's going to be inaccurate, but the smaller we make this jump each time, the better and more accurate our solution is going to be, the closer it will track the original curve. So making delta x small, so by repeating the process, we can find a bunch of points to approximate our curve. Okay, but notice that, we knew the first point exactly. After we did an estimate, the next point was off. And then we're using faulty information. This isn't actually on the curves. And we're making our next approximation based off the first approximation. Then we're going to make our third approximation based on the second approximation, which was based on the first approximation. And so as you go through these points, what you expect to see is sort of an accumulation of error. Each successive step adds to the error of the solution, of the approximation. So eventually you would expect that our answer is probably not going to be very good. Okay. When I talk about error, I want to talk about it a little bit more carefully because there are some important terms that come up. So let's talk about this idea of error in these methods. There's going to be something that we call the absolute error and then something that we call the relative error. And so let's define both. The absolute error is literally just going to be the difference between the true curve, the hypothetical true curve, and our solution, our guess. So it's just going to be the difference between the true answer and our approximate answer. So the absolute error is the difference between the true solution, so the true curve, and our approximate curve. At a given x coordinate. And I'm suggesting that over time you expect more often than not this absolute error will increase as we go from our first point that's right on the money to the next point, to the next point, to the next point, to the next point. Our solution, or our error will get bigger and bigger and bigger. But What we'll usually care about more than absolute error is what's called relative error. So let's define that. The relative error, let's do these bullet points here so they're easier to read. The relative error is basically the proportional size of the error. So it's the proportion to the sort of actual magnitude of y. We're looking at this tiny difference between the true value of y and our approximate value of y, and we're going to compare that to the actual value of y over here. So the true actual value. We're going to compare it to the real value of y. And the reason is, an error of 0.1 is really significant if we're kind of zoomed in and looking in the neighborhood of y equals 0. 0.1 could be significant. But an error of 0.1 is insignificant if we're up talking about a y value that's like y equals 1,000,000. The difference between 1,000,000 and 1,000,000.1 isn't that significant. But the difference between 0 and 0.1 is potentially quite significant. So the relative error is what I'll just call the proportional error. And it's easier, so the proportional size of the error, I should say. And so we would say that it's equal to the absolute error divided by the actual value of y, so the true value. We'll talk a little bit about this. I'm going to assign a project for you guys where you will implement Euler's method. I will give you what's often referred to as pseudocode to kind of guide you through how you would set it up and just leave you guys just a few little blanks to fill in. And if necessary, I'll maybe even make a separate video for that specific problem if people are struggling on it. But I'll talk about some of the ideas of error and relative error in that problem. We'll just look at some of those things and kind of keep track of what's happening to the error as we jump through multiple steps of Euler's method. So we'll talk about that in the project. I kind of want the project to be a learning experience in and of its own. So I don't want to talk about these errors too much more other than to just define them. And then again, we will investigate kind of how these things work and why we care about them in that project. But let me just mention this method, Euler's method, is just one of many different possible numerical methods for solving a differential equation. In fact, it's one of the simplest, if not the simplest. And it also is one of the worst. And when I say worst, what I mean is the error winds up being the worst. So there are other more accurate methods, and they actually all wind up involving some ideas from the end of Calculus 2 when you talked about Taylor series. So at some point, maybe towards the end of the semester, that'll be worth delving back into if we have time at the end of the semester. But for now, just know that this is one way to get approximate solutions to differential equations that can't be solved with pencil and paper. And you'll learn a lot more about it when we do our project. So before I throw you into the water to sink or swim on the project, let me just talk a little bit about how we can implement Euler's method. The way I've written it out here is basically one step of Euler's method, but the idea, as I've drawn here, is that we want to repeat this step multiple different times. And so let me talk about how we can actually implement Euler's method. Implementing Euler's method. So in the example above, I used, for our independent variable, I used x. And that's totally fine. You can use x. But one way to think about it also is oftentimes a differential equation that depends on time. And you can think about stepping through, instead of different x values, you could think of it as stepping through different t values, from starting at time 0 to time 1 to time 2 to time 3, and so on and so forth. So let me just talk real briefly about how we could implement Euler's method. So let's just write it down. Euler's method states the following. It basically says, so let's just copy, which one should we copy? Let's do, instead of this one, because it was specific to the point x naught, y naught, let's go back up to the generic one up here. So let's write this one down. And I'm going to change all the x's just in the sake of this, because I think it's easier for people to imagine if we talk about sort of stepping through time as opposed to stepping through space with the values of the independent variable. So all those x's are going to change to t's. That's the only difference. So I'm going to say that y at some value of t plus delta t is given by the value of y at the current time plus this function of t and y delta t. So all I've done is literally come and copy this equation right here and switch all the x's to t's. Okay, so this is Euler's method. All it's saying is that if we know the current time, so we've visualized this as a linear approximation here. So this is the geometric interpretation. But now I want to think about it from a different perspective, because I think this perspective is easier for some people. I want to think about this as stepping through time. If I know the value of y at a given time t, I can figure out what the value of y is at a later time, t plus delta t, by adding a certain quantity to the current y value. And it turns out that quantity is this amount. This amount, if you think about this, this is a slope. So you could think of this as sort of a rise over a run. We're multiplying it by a delta t, which is basically an amount of run. And when you multiply these, you get a bit of rise, right? So you multiply these and you get a bit of rise, which makes sense. We're adding to the existing y value some little amount of rise, and maybe that rise is actually a fall. Maybe it's if the slope is negative, we're going down instead of up. And we find a new value of y at some later time, but this is kind of how it works. If we want to repeat this process, it helps to keep track of the times. So basically, we'll start with some initial value. And maybe that is indeed what we call t0. And the next point that I want to check is going to be a later time, and we'll call it t1. And t1 is going to be the original value of t, so t0, plus some small amount of time that's elapsed. And then after that, we'll want to add another delta t. So this is, again, the process that I kind of indicated here as we increasingly add more and more delta x's. Now we're adding more and more delta t's. So here's after 1 step, here's after 2 steps, 3 steps, 4 steps, and so on. And I'm going to give names to these values. So the first one is t0. After 1 step, we're at time t1. After 2 steps, we're at time t2. And t2 is going to be, you could think of it as t1 plus some delta t, which is equivalent to t0, the original t, plus we've now taken 2 steps in time, 2 delta t's. And t3, which will be the time after, it'll be the same as taking 1 step from t2, or taking 3 steps from the original value of t that we started at. And you can see this going on sort of indefinitely. But the subscripts that I'm using here are what are going to be called indexes. So we're indexing time, and the index tells us which time step we're at. It tells how many steps we've taken. Since we started. Okay, so basically what I'm going to do is use the initial value of time and plug that in to get our value of y at t1. Once I know the value of y at t1 or our guess for it, I'm going to plug that value of y in to get our guess at t2. Once I know t2, I'm going to use that value to get our guess for t3. And so here's how that will work. So our first step, let's say we have the initial condition, and I'll write it down here. So our initial condition, let's assume our initial condition was that basically y of t0 was some value of y that we just called y0. So these indexes or indices will match the ones for the t's. So t0 goes with y0. T1 and y1 will go together, and so on and so forth. So the first step is we know the solution passes through the initial condition. So it goes through the point y0, or sorry, let's do it in the correct order here, t0, comma, y0. To get the next value, what we do is plug this in. So I'm going to write down the different values of time and the corresponding y value. So here's at t0, we know the y value is y0. What is it going to be at t1? Well, at t1, we're going to get the value y1 by looking at our approximation here. So what I'm suggesting is what I'm calling y1 is going to be at t0 plus 1 delta t after. I'm plugging this thing in to the value on this side to get what y1 is. So the y1 value is going to be, we take the old value, y0, and we add f at t0, y0, whatever that slope is, times delta t. And that'll give us our guess for what y1 is. Once I know y1, and I know that y1 occurs at time t1, how do I get t2? So at time t2, I will get the value of y2, and I will get the value of y2 by plugging in y1. So I'll say we're going to go from our old guess y1, and we're going to add a little bit to it. I'm going to figure out what the slope is at time 1 and plug that into the equation to get our next guess. And so what you can see is basically by repeating this pattern over and over, we can start to see the pattern emerge. This term is always going to be delta t because we're taking a step of size delta t every single time. We're going to basically plug into the initial, so we know this point, the point t0, comma y0, and we'll use that information. These are the values that get plugged in here and here. Once I use those values to get my guess for y1, then I'll use the values of y1 to plug in here and over there. And I'll use that guess to formulate my next guess for y2. Once I have y2, I would then implement those in this position and this position to get y3, and just repeat this over and over. We can see that this process can be repeated many times. And this is where the computer comes in. It's really nice if you can have the computer do all of this for you. So what we'll essentially do is put this into some sort of loop. And what we'll do is basically run through the loop to get our new guess for y. Once we have that new guess for y, we'll run through the loop again with that new guess for y to get our extra new guess for y. So we'll plug in y0 to get y1. Well, once we have our guess for y1, we'll plug that back into our formula in the loop to spit out y2. Once we have our guess for y2, we'll run through the loop again and use that approximation to spit out y3. And that's how we'll do this over and over. So if you want to think of it in terms of pseudocode, very, very basic pseudocode, what we'll do is we'll sort of start with a, basically set t0 and y0, set our initial point, and then we'll run through some sort of loop. So you can use a for or a while loop, depending on what you're more comfortable with. And you'll basically say from for or while starting at t0 and running off to some later time, let's just say tn. run through the loop n times. We want to get to some later time. And what we'll do is use our indexes. We'll basically say, let's do, take the current value and say, right, if we want the next y value, we'll take the current value, and what we'll do is multiply delta t by f of t current and y current times delta t. And then we'll end our loop. And then actually other thing I need within the loop is basically we'll record this next value of y, add it to our list of x and y coordinates, or in this case, t and y coordinates. So once we have our next value of y that goes with the corresponding next value of t, record those somewhere, and then we'll change it so that we'll say the current value of y is the next value of y. So we're going to update our current value of y. Initially, our current value of y is t0. After we run through it one time to get y1, what we'll say is let's change it now so that we're thinking of as the current time is really going to be our y1. And then we'll plug in y1 in all of these positions to get y2. And once we have that y2, we'll say let's pretend y current is now y2 and plug that in over here and go over and over. And then we'll end everything. So as long as we keep track of all the t and y values, we're good to go. And then we'll plot them. And so I will give you, again, some hints for the details of how to do this, but hopefully your minimal programming experience will let you set something up like this. And I will, again, give you a lot more instructions and details in the actual programming assignment. But this can give you a sense of how you might program to automate Euler's method. The original thing that we called Euler's method only gives you one step. And to automate it, you take the output and have that output be the next input that's used to get yet another output. Then use that as input to get yet another output, and so on and so forth. And repeat this over and over, and you eventually get a series of points that approximate our solution curve. So good luck. Let me know if you run into troubles. I'm more than happy to help on the programming assignment. So just keep me in the loop. You're welcome to work together as long as you're each doing it on your own. You feel free to bounce ideas off of each other. Feel free to look at somebody else's code. But I really want you to go through the process of writing it yourself. So please don't just copy and paste somebody else's code. The point is to get a little practice in coding and to tie it to some mathematical ideas. And so it's really all in the practice. Okay, good luck.